In this video, we're going to look at another example of volumes of revolution using the washer method. The question here is to find the volume of the solid obtained by rotating the region bounded by the curves y equals x squared, the parabola y equals x squared, and the line y equals x, about the line y equals 2. So the first step, as usual, is to find the points of intersection that defines our region. So we have y equals x and y equals x squared. We'll make y equals y and solve for x. So we get x is equal to x squared. Bringing everything to one side, we get x squared minus x is equal to 0. Now factor x out, we get x times x minus 1 is equal to 0. And let's solve for x. We get x equals 0. And we get x minus 1 equals 0. Solving for x, we get x equals 1. So we have x equals 0 and x equals 1 as the x coordinates of the intersection. Let's also find the y coordinates as well. Let's plug in x equals 0 into y equals x squared, and we get y equals 0. Let's put x equals 1 into y equals x, and we get y is equal to 1. So the points of intersection are 0, 0, these are xy coordinates, and 1, 1. All right, so now let's sketch the bounded region and a typical washer. The most important thing is getting the radius of rotation, and this is a part that's, a lot of students make mistakes on that because the integration usually is secondary, it's not too difficult, but it's really important to get the right radius of rotation. So I'm going to really emphasize this at the risk of repeating myself. So what we have here is we want to define the outer radius. How do you define the outer radius? The outer radius is going to be the distance from the axis of rotation to the farthest point on your rectangular element. So you can see how if we take the whole distance from y equals 2 to the x-axis is 2. The distance from the bottom of the slice is y equals x squared. So if we take 2 minus the y value corresponding to the parabola, 2 minus y, that's going to give us 2 minus x squared. This is the outer radius. The radius outer is 2 minus x squared. The inner radius is the distance from the axis of rotation, which is y equals 2, to the closest point on the rectangular element. That's going to be 2 minus x. So it's this distance that we're after. That's 2 minus x. So radius inner is equal to 2 minus x. Very important that you convince yourself that this is the correct radii, radius outer being 2 minus x squared and radius inner being 2 minus x. The important thing to realize is that we're on a coordinate system. So what we're actually doing is radius outer is 2 minus the y value corresponding to the parabola. And the y value corresponding to the parabola is x squared. The inner radius is 2 minus the y value corresponding to the line y equals x. And we have the drawing here. So there it is. Okay, now let's define the radius outer, radius inner, the cross-sectional area, and the washer volume, and the total volume. Let's set up the question. So radius outer is a distance from the axis of rotation to the farthest point on your rectangular element. That's 2 minus x squared. That's this quantity here, 2 minus x squared. From here to here. That's the outer radius. The inner radius is 2 minus the y value corresponding to the line, so it's 2 minus x. That's the inner radius is 2 minus x, the outer radius is 2 minus x squared. So that's radius outer, radius inner is equal to 2 minus x. Now let's talk about the cross-sectional area. Cross-sectional area. The cross-sectional area is going to be pi times the outer radius squared, so radius outer squared, minus radius inner squared. So the area is equal to pi times radius outer, we defined it as 2 minus x squared, squared radius, minus radius inner, which is going to be 2 minus x, all squared. So radius outer squared minus radius inner squared. Pi times that, and we get the volume of the cross-sectional slice. I should say the area of the cross-sectional slice. So now let's find the washer volume. Okay, differential volume is equal to pi times radius outer squared, 2 minus x squared, all squared, minus 2 minus x, all squared, times dx. That's a typical washer, and then we're just going to add up all these washers, add up the volume of all of these washers to get the total volume. So the volume is going to be the integral of dv, integrate from 0 to 1. So it's going to be integral from 0 to 1 pi times 2 minus x squared, all squared, minus 2 minus x, all squared, dx. All right, so that's the volume, and we can move the pi out. Pi is a constant. It just passes through the integral, so let's write it in a different way. Pi times integral from 0 to 1. These are x values. X is 0, x equals 1. Outer radius squared, that's 2 minus x squared, all squared, minus inner radius squared, 2 minus x, all squared, integrated with respect to x. Now the job is just to integrate this. That's going to be pretty easy, and we'll do that in the next step. So we're now going to do step 3, which is set up the definite integral. So step 3, set up definite integral, and solve. Solve for the volume. Solve for volume. All right, the volume is equal to pi times integral from 0 to 1, 2 minus x squared, all squared, minus 2 minus x, all squared, dx. Let's simplify the integrand. We're just going to open up the brackets. I'm just going to use this algebraic identity, a minus b squared. That's going to be a squared minus 2ab plus b squared. So volume is equal to pi, integral from 0 to 1, and 2 squared is 4, minus 4x squared, plus x to the 4th, minus 2 squared is 4, minus 4x, plus x squared, and let's close the brackets here, dx. We'll simplify the integrand and then integrate using the reverse of the power rule. So let's open this up. We get 4 minus 4x squared plus x to the 4th. Distribute the minus sign. We get minus 4 plus 4x, because minus times minus is plus, and minus x squared. It's very easy to make a mistake when you're distributing the minus sign. So it's really important to have these brackets here and distribute that minus sign. Now we have to simplify this. So 4 minus 4, that cancels out. And what do we get? Volume is equal to pi, integral from 0 to 1. We have x to the 4th. And we have minus 4x squared minus x squared. That adds up to minus 5x squared plus 4x. And let's integrate this with respect to x using the fundamental theorem of calculus. So using the reverse of the power rule, then we'll evaluate it using the fundamental theorem of calculus. I'm getting ahead of myself here. So what is the integral of x to the 4th? That's x to the 5 over 5, reversing the power rule. What's the integral of x squared? Well, that's x cubed divided by 3, reversing the power rule. 5x cubed divided by 3, integrating term by term. What is the integral of 4x? That's going to be 4x squared divided by 2. Evaluate it from 0 to 1, and we're now going to apply FTC to solve for the volume. All right, so the volume is equal to pi times x to the 5 over 5 minus 5x cubed over 3 plus 2x squared, evaluated from 0 to 1. So the volume is equal to pi. Plug in the upper limit, we get 1 over 5, applying fundamental theorem of calculus, minus 5 over 3 plus 2, and minus pi. Plug 0 in, we get 0 minus 0 plus 0. So let's simplify this. Let's add up these fractions. We could take a common denominator. The common denominator is 15. 5 goes into 15 3 times. And 3 goes into 15 5 times. 5 times 5 is 25. And 1 goes into 15 15 times. 15 times 2 gives us 30. So that's going to be pi over 15. And we have 30 minus 25. That's 5 plus 3. That's 8. We get 8 pi over 15. This is a volume of solid of revolution. And if we decimalize this, we get 1.68 unit cubed as the volume of the solid of revolution. So let's go back into the picture to show the volume. So basically, when we take this region and revolve it about y equals 2, we get the volume that we find here. Here it is. Or the exact version, which is here. All right, thank you.